But inductors and capacitors are not used in isolation from other electrical and electronic components.
When used in combination with resistors and capacitors, for example, phase differences can be used to provide some interesting effects. For example, the color signal in this VCR is based on the phase difference between two signals. You'll learn about these in your study of advanced AC circuits.
It's important for you to have an understanding of these two types of reactance, because when you get to AC circuits, you'll see how reactance interacts with the circuit resistance in certain predictable ways, which become a critical factor in the design of circuits.
For now, keep in mind that both inductive reactance and capacitive reactance are measured in ohms, and that in the capacitor, the capacitive current leads the voltage by 90 degrees, whereas with an inductor, the inductive current lags the voltage by 90 degrees. This difference can be remembered with this memory aid, Eli the Iceman. Eli reminds you that in a purely inductive circuit, L, the voltage, E, leads the current I by 90 degrees, whereas ICE reminds you that in a purely capacitive circuit, C, the current, I, leads the voltage E by 90 degrees. As you continue your study of electricity and electronics, you will find that the concepts you have learned here will play an increasingly important role. You now have a good idea about the various roles that capacitors, inductors, and transformers perform in AC circuits, and you also have an awareness of the effects of reactance.
Just as in DC, the fact that power is drawn from a source and does work in a circuit is important in AC. Let's consider some types of power: reactive, true, and apparent power.
The power consumed in a purely resistive circuit is the product of the voltage and the current. You know this formula to be P equals I times E. However, power is a more complicated issue in circuits containing reactive components, because they not only draw power from the AC source, they also return power to the AC circuit as well. In an AC circuit containing capacitance only, for example, energy is first stored in the electric field within the dielectric. But this energy will also be returned to the source when the capacitor discharges. In a purely inductive AC circuit, on the other hand, the power that is used to build the electromagnetic field will be returned to the circuit when the field collapses. Both of these examples point out one important type of power known as reactive power. The reactive power is simply shuttled back and forth between the source and the load, so the net power consumed in a purely reactive circuit is zero.
A second type of power, true power, is the actual power used by the resistive elements in the circuit.
True power calculations are more representative of the actual power consumed because they take any existing phase differences between current and voltage into account.
In all electrical and electronic systems, it is the true power that indicates the work done in the circuit. Ideally, in terms of performing useful work, all of the power transferred to the load should be true power and none of it reactive power. But from a practical standpoint, many AC loads contain both resistive and reactive elements. True power calculations take both of these elements into account, and so are somewhat more complex than simple resistive power calculations. A wattmeter can be used to measure true power.
A third type of power, apparent power, is equal to the product of the effective voltage and the effective current. Apparent power calculations ignore any phase differences that may exist between current and voltage. And while the watt is the designated base unit of measurement for true power, the base unit used for apparent power is the volt-ampere. Let's look at an example using apparent power. Suppose that in this inductive circuit, an applied AC voltage of 100 volts causes a 10 ampere current to flow. Assuming an ideal inductor, that is, one that has no resistance, the true power in this circuit is 0 watts, since the inductor returns the same amount of power to the circuit that it draws from the source. But ignoring the phase difference, the apparent power in the circuit is found by multiplying 10 amps by 100 volts, which would be 1,000 volt amperes. Don't forget that the volt ampere is the base unit of apparent power. In AC circuits that may contain capacitors or inductors, the idea is to deliver only the power needed from the source to the load.
Let's see how in a reactive circuit, power is shuttled between the source and the load, but no useful work is done.
The reason for this is that power is equal to the product of voltage and current. Looking at this graph showing voltage and current 90 degrees out of phase, you can see that multiplying a positive voltage by a positive current results in a positive power curve. A positive power curve means that power is being delivered by the source to the load. A positive power curve will also result after multiplying two negative quantities.
However, it's important to realize that multiplying two quantities with unlike signs produces a negative quantity.
When a negative current is multiplied by a positive voltage, a negative power curve results. Similarly, when a negative voltage is multiplied by a positive current, you still get a negative power curve. A negative power curve means that power is being returned to the source by the load, rather than being used by the load.
A source may be delivering large voltage and line currents, but if the load is purely reactive, no electrical work will be done.
If, on the other hand, the voltage and current are in phase, as shown here, the resulting power curve will always be positive, meaning that power delivered by the source is always being consumed by the load. The reason why the power curve is positive is because when the voltage is positive, so is the current. The product of two positive numbers is also positive. When the voltage is negative, so is the current. Remember that the product of two negative values is also positive. So in AC power distribution, the goal is to keep the phase relationship between voltage and current as close to zero as possible.
Stop the program and complete activity number 4. When finished, continue watching the program.